Good morning. Today we are going to study tracking radars. Here is the outline of the lesson. We'll be talking about operation of tracking radars, and then we look into tracking radar types, sequential lobbing, conical scan, monopulse, and finally we'll be talking about limitations to the accuracy of tracking radars. Okay, as we have studied in previous lessons, we measure or estimate the distance to a target by using radar systems, and we can measure the speed of the target, and we can also measure the angle of the target. Moreover, we can estimate the future position of the target once we estimate the exact position and calculate the trajectory of the target. In tracking radars, there are some additional requirements. We need to see high resolution in both range, angle, and Doppler space. In search or surveillance type radars, we may not need such a high resolution in either range, angle, or Doppler. And this high resolution might provide less echoes from the clutters around the target because we focus the energy. For example, in angle case, we focus energy on a specific volume in space, which means that the echo signals from the objects around the target will not be captured, will not be visible to the radar. Usually, a tracking radar is connected with a surveillance radar or search radar. Once the search or surveillance radar detects a critical target, which could be tracked, then it passes this information to tracking radar, and then tracking radar get the positional information from the search radar and then initiate a track, acquisition, and then track. Okay, how about tracking radar types? We'll be talking about basically 4 types of tracking radars. These are discussed in detail in the textbook. Some are very old, some are currently used in most of the radar systems. Since this is an introductory course to radar systems, we simply try to give the overall systems, not the current systems only. Okay, the first tracking radar type is single target tracker, STT. It continuously tracks a target as it is engaged with a single target. Its data rate is quite high. In a second, it can report 10 observations. And it has a closed loop system, which means that it captures a signal and analyze the angle error signal and then position the beam to the target. It's widely used in tracking of aircrafts or missile type targets in military weapon control systems. An example of this will be for C-band AN FPQ6 this is a designation used, especially in Western countries. This is usually studied in electronic warfare systems. I'm not going to go into details of this. You can easily find this from internet. The next tracking radar type is automatic detection and tracking. It's a system that that's designed to cover a specific part of the air. So you can, for example, cover a region, let's say from 120 degrees to minus 120 degrees to plus 120 degrees. So it's about 420 degrees volume in azimuth and full elevation angles. So then this ADT is used in such operations. It's widely used in military surveillance and modern air traffic control radars in the airports, for example. Its rotation rate might be from several seconds to some 10, 12 seconds, and it provides lower data rates, relatively lower data rates compared with SDT, but it can track multiple targets. It might sometimes go up to thousands of targets. It uses open loop data control. So this means that antenna position is not determined according to the received signal. And in that way, with this property, this is quite different from the SDT operation. The third tracking radar types is phased arrays, which has been very popular, and it's quite complicated technology. It's a combination of somehow SDT and ADT. It provides high data rate, and with this high data rate, it can track many targets together. The idea here is about electronically steered arrays, which is a complicated system. So it generates beams in very short times and tracks multiple targets simultaneously. Air defense weapon systems such as Patriot, most of the modern air defense systems use such a phased array system tracker. Track while scan, TWS, it's again covers a limited angular sector to maintain tracks. It has moderate data rate. It may track multiple targets in the coverage volume. All air defense radars and aircraft landing and airborne intercept radars use this track while scan technology or tracker. Okay, here we see two examples. It is the system that I have talked about in previous slides. And this is an electronic scan phased array where beams are generated by phased arrays. It can track multiple targets and it provides high data rates. So this is one of the critical technology that many of the countries couldn't have. Okay, here I just want to show you slide about a specific radar, AN/APG66 version 2 and 3. It can be found in internet, so this is not specific to this course actually, but it's used in F-16. This is a multi-mode weapon control radar. It uses pulse Doppler principle, and it has search and track mode, track while scan, air combat search, or air-to-air engagements. It has continuous wave illumination capability, and it can support these missiles. The frequency operational band of the radar is X-band from 6.2 to 10 gigahertz baseline, and it's usually 8 to 10 gigahertz band. It uses traveling wave tube in the older versions, but in new versions there are solid-state power amplifiers. And it covers 120 degrees in azimuth, and it may have some angular coverage depending on the modes that are chosen. Its range might be from several tens of kilometers up to 150 kilometers, depending on the operational modes. Okay, next, we are going to talk about tracking methods. The previous discussion was on tracking radar operations or tracking radar types. Now we're talking about trackers. So how we implement tracking simply. As you might estimate, if you want to track a target in space, there should be at least 3 beams. So if we have a target here, we have to generate 3 beams like this. This is the footprint of the beam 1, beam 2, and beam 3. So by looking at the difference of the signals, any 2 beams, okay, we can position the direction of the beams, so direction of the antenna. If the object is moving in that way, then we expect that this difference will be higher, right? And this difference will be higher, then this difference will not be changed or very small. Then we move the antenna, if this is the bore side of the antenna, to up to get echo signals. So that's the idea. If we use more than 3 beams, then this process will be easier to implement. And in practice, there are usually 4 or more beams. There are 3 tracking methods: sequential lobbing, conical scan, and monopulse. Will be now in the remaining of the slides talking about these tracking methods. Okay, as we have shown in previous slide, we need several beams to track a target. And if we consider single plane, so in perpendicular plane, let's say, we have a target here, and we create 2 beams. This. They should be overlapping, okay? Now, these are the centers of the beams, let's say. So you can imagine that we got a beam just like this, and another beam like this in space. So if we look at the center of these beams, we can take a reference center, which is the bore side of the antenna. We can show these beams on this UC plane. They are overlapping, you see, and their bore side here is the bore side of the antenna actually. So beam is moving or antenna is moving, whatever you use. But there is a bore side where the two beams are squinted from each other. Okay, there is an angle between them. So what happens then here? If we look at the signal power here, for example, they're almost similar. When the object, when the target is moving up, let's say this is the next stage or next position of the target, then if we look at the beam powers here, the echo signal power, you see that the power coming from the beam 2 is greater than beam 1. Okay, so this means that I have to move the antenna, so the bore side, up in order to try to get almost zero difference between two signals. So we try to minimize the signal difference simply. In order to minimize signal difference, then we move the bore side of the antenna accordingly. Okay, this is simply a closed loop system. We measure the signal, get the difference. If the difference is high on the side of, let's say, beam 2, we move it up. If this the signal is, the signal coming from 1 is greater than 2, then you move it down. This is single plane. When we extend this and add another pair of beams, just like this, then we can compare these two and these two to move to the antenna to the right or left. And we can check the signal powers coming from these two and these two, and then again move it up. Okay, so we can simply track a target in 3 dimensions. Okay, now here the squint angle, so how much the beams are separated from each other, okay, the angle between the beams, which is called squint angle, is critical. How do we choose this? If we choose this very small, then we might get a very little difference between the signals, right? Because the beams are closing to each other, so the crossover, the difference, the signal power here, the crossover will be smaller if they are close to each other. They are overlapping, so the squint angle is small. When we choose a larger squint angle, then this difference will increase. This may be good in one sense because we couldn't miss the target as the beams are separated enough. But on the other end, when we look at the signal power in here, then the measured signal power, let's say here, it's going to be small compared with the squint angle with a small squint angle. Okay, so the value of the squint angle is critical. Then we have to think about that, and we'll be showing that in later. That there is an optimized value in most of the trackers. Okay, it was the idea of how to track a target in 2-dimension and 3-dimension. Again, we should have at least 2 beams to track a target in one plane. And for 2 planes, we have to have at least 3 beams. And in practice, there are usually 4 or more beams to track a target in 3D, so in 2 planes. Again, by the way, let's go back to the planes. If this is the Earth reference, and this is taken the azimuth, and this is taken elevation. So whenever we are talking about tracking, we should consider elevation and azimuth planes. Okay, so then we have elevation and azimuth angles. Okay, sequential lobbing. This is the first type of tracker, sequential lobbing. Okay, or lob switching. This is the simplest case. We have 2 beams, and we simply switch between the beams. Okay, so we are not moving anything. It might be stationary. We simply emit signal from the beams in order. So let's say 1 millisecond in one beam, and 1 millisecond in another beam, and so on. So we get the signals, and then get the signal amplitude differences of the 2 beams, of the 2 measurements actually, and then determine the position of the target. I mean, the motion, the directional motion of the target. It's shown here simply. For example, if the signal amplitude coming from position, beam position 2, so beam, second beam, let's say x2, and beam position 1, x1, apparently, if the target is simply somewhere here, okay, where we got the crossover here, you see, which means that the signal power coming from the beam position 2, so x2 is greater than x1. So since x2 is greater than x1, then we have to move the antenna to right, okay? In the next position, we do another measurement and then move it. Do another measurement and move it, okay? Of course, this is very, high-level description of the operation. In reality, there are too many parameters here, and you have to spend lots of time to design such a simple system. For 3-dimension, as we said earlier, we use more than 3 beams for tracking in azimuth and elevation. Usually there are 4 or more beams, and one here there are 2 figures showing some antenna systems to generate those beams. Probably the most common system that we can see in daily life is a parabolic dish. On the roofs, for satellite systems, we have antenna system. Usually it has a parabolic dish, and it has parabolic dish is illuminated by a feeder, okay, which is an horn antenna. So if there is a signal coming from space and hit on this parabolic antenna, and then directed into this feeder, this horn. Okay, so the horn is positioned such that it collects all the energy reflected from this parabolic dish. So the parabolic dish and so the reflector antenna and the horn antenna are simply designed to collect all energy reflected from the parabolic dish. So the position of this feeder is then critical. Now, suppose that we put another feeder here, okay? Or let's say first think about the opposite. Let's say we do not have any signal coming from space. Instead, we create a signal, generate a signal from this, let's say, signal generator. In the laboratory, you know how to generate this, just using a VCO and a power amplifier, then you can create it. Now apply this to feeder, this horn. Then horn will simply, it has a beam width, just like this, okay? It covers the area here. So something like this. So it emits signal into this reflector. Once the signal hits on this reflector, then they will be reflected. Okay, just like this. So we got a beam. Now, if I position two feeders, okay, so this is an example. Yeah, for example, this is feeder 1. Can you see that? Let me make it red. Okay. On the this figure we are talking about, here there is a feeder, another feeder, and another feeder. So they're aligned so that due to the difference between them, there is going to be 3 beams created by the reflector. Okay, so we can simply show it here. So here is my reflector, and there are 3 feeders in here. Since they're positioned at different points over the line, then we'll have different regions of the reflector we illuminate, which means that there is going to be 2 or 3 different directions. So each horn will emit signal, equal signal actually, the same signal, but due to the position of the feeder, then there are 3 beams created. Okay, so beam 1, 2, and 3. Okay, so if we take this bore site, for example, for this 3, for this 2, then we can measure target here or here, for example. So by increasing the number of horn antennas on a parabolic dish, simply we can create multiple beams, and then if we switch between these beams, then we can implement sequential lobbing. Okay. Now, in the next stage, why am I going to switch between the beams? Instead, why am I going to use some, continuously changing beam positions. I mean, if I do this, if I rotate the antenna continuously, I can create beams, continuous beams. Okay, then this is called conical scan. Conical scan. So in conical scan, we have to move antenna or feeder, but there should be a motion. Okay, in sequential lobbing, there is no motion, right? I mean, the beams are not moving, they're fixed, but we move the antenna bore side. Now, in conical scan, we move beams. How? We simply rotate the antenna. Once we rotate the antenna, since this is slanted, so squinted from the bore side, so let's see, this is the B, okay, this is the uh, rotation axis, okay, and here is the beam axis. So the difference here is called squint angle as usual. So we simply create a beam and then rotate it. Okay, so here is the second position, third position. So continuously moving, continuously rotating these beams is simply called conical scan. Okay, now in this case, we have continuously measured signal, and the amplitude of the signal will be related to the rotation rate of the beam, so the antenna, okay? And the amplitude modulation then simply depends on the angular distance between the rotation axis and the target location. One example of such a system is shown in here, Landroll. That's a J-band radar with 3 different modes: guidance, tracking, and acquisition. So from 25 kilometers up to 35 kilometers. Here we have an example, a problem from the textbook. Here we'd like to actually give emphasis on automatic gain control, AGC, which is a very critical block in spatial tracking radars. It's used in almost all radars, but in tracking radar, that's quite critical. And in this problem, you are asked to compare the power, echo signal or target echo from targets at different distances. If it is in 2 nautical miles or if it is in 100 nautical miles, so how much difference in power we expect? Here there are 2 things, of course. One is the distance, the other one is the radar cross-section of the target. So you will see that the difference of the received power is quite big. So there should be something that you should use at the receiver to balance this difference. Okay, that's called automatic gain control. Okay, AGC. Please use this figure and that table to answer or to solve this problem. In office hour, you can ask your questions regarding with the problems, as you know. Here we have another example. That's a semi-active missile. That's an example of, again, tracking radar. We have an illuminator. Here is the target, and here is the missile system. as you see, illuminator and missiles are not co-located. They're at different positions. And the goal of the illuminator is to transmit signals continuously or interrupted continuous wave. So interrupted means transmit some and then wait, and transmit some and wait. In this way, the emitted signal will hit on the target, but it's collected by the missile, not the illuminator. Okay, and there is usually a link between the illuminator and the missile, a communication link. So it's just like a radio link or telecommunication link, which gives some reference signals from the illuminator. So they're coordinated. Okay, and there is a radar, usually on the nose of the missile, which simply collects the echo signals transmitted by the illuminator. Okay, so this illuminator and missile radar work together. They're coordinated, and this is called semi-active missile. Since the missile does not emit any energy, then it's not possible for the target to detect the missile. It can detect the illuminator only. So then if there could be an action from the target, it should be toward the illuminator, not the missile. Okay? And there are some techniques in here, conical scan, monopulse, LoRa. I'm not going into details of this, just as an example of tracking radar. Here is a missile seeker from internet. I just got it. You can see here the antenna that we have talked about previously. As you see, there is probably a feeder here. And here is you see the shape of this antenna. It's just like a satellite antenna. So it's likely that this is moving in that way, or maybe circulating, rotating, and then try to hit the target. Okay, let's have a break here. Okay, next then. That's one step further, active homing. So this was, as you might remember, semi-active missile. Here we got active homing. SAM or other systems use this type of missile. Here there is a active seeker. So remember that in semi-active missile, there was a passive seeker. Now there is an active seeker. Active seeker means a tracking radar. Passive seeker is also a tracking radar, but that's that does not emit any energy signal. These are fire and forget type missiles, usually costly, and they use monopulse seeker that we'll be talking about next stage. There may be a guidance system, actually the door guidance system. It can be guided to the target area, and then it can simply activate the seeker tracking radar, and then using this active seeker, it hits the target. Okay, let's see monopulse tracking. That's the last tracker and the most advanced tracker among the three trackers. It uses simultaneous beams, and it uses even at least theoretically, single pulse to measure the the position, or to estimate the position of the target. That's why we call monopulse. So in previous trackers, as you might remember, we have to rotate the beam, we have to switch the beams, and then collect the echo signals, and then measure the differences, and then make a decision, and then rotate the antenna. Now here, you don't need any of this. You just take one pulse and then measure it, and then position the antenna. One pulse, measure it, and then position the antenna. Okay? There are two types of processes in monopulse: amplitude comparison or phase comparison. In amplitude comparison, we use the echo signal amplitudes, and then the decision stage uses the amplitudes of the echoes, and then make a decision, and then rotate the antenna. In phase comparison, it uses only the phase of the signals. Okay. Now let's just imagine two beams, again squinted beams. When we add the beams up, we'll get the sum signal, and then if we separate the beams enough, we get the difference signal. Okay, these sum and difference signals are used in monopulse processing. On the right hand side, you see a picture showing an MPS 39 C-band phased array monopulse. It's a multi-object tracking radar, missile range instrumentation radar. It's one of the I think oldest monopulse phased array systems. Okay, let's see a block diagram of monopulse radar for amplitude comparison. And we consider only elevation. So here is the elevation. There are two antennas, so two beams. And here is the transmitter. The signal is simply passed through a duplexer. Duplexer, as you might remember, is a three-port device which allows a signal coming from the transmitter to the antenna. If there is a signal coming from the antenna, it passes through the duplexer and fed to the mixer. If there is any signal, if we talk about the signal between the transmitter and receiver, there is an isolation. So no signal is allowed to go from transmitter to receiver or from receiver to transmitter. That's how duplexer works. So from this side, then we got both transmission and reception. And there is another receiver channel here. So there are two channels, channel 1 and channel 2. And these are called sum channel and difference channel. Okay, how do we do this? By using a hybrid junction. Hybrid junction is an interesting microwave usually device. It has 4 ports here, as you can see. Usually this port and this port are input. So if we apply 2 signals from port 1 and 2, I got the sum signal in here and different signal in here. Okay? Or if I apply a different signal here or some signal from here, then I will get 2 such signals at this outputs. So in that way, we can use this hybrid junction as again, just like duplexer, as a transmit and receive operation for the sum channel. Now, what we'll get then? If I got the some signal here, it is first mixed by by the local oscillator, which is common to the difference channel. Again, we got the same mixer in here, and we got IF amplifier. These are usually match filters. Okay. And then we got a phase sensitive detector. So the phase between the two signals are processed in here, and then angle error signal is extracted. Meanwhile, the some signal is used in an amplitude detector, and then the range to the target is measured. So from here, we got the angle error. From here, we got the range. And these two are fed to the antenna system again. If there is a need to rotate the antenna, position the antenna, then it's used. Okay, this is single plane. When we extend this, so if you put two more antenna here, let's say C and D, then we can cover azimuth too. So here is the three-dimensional, so two planes, monopulse radar. As you can see, we have four antennas in here, and we got again three channels, one for sum, the other two are for difference. One for elevation, so this is elevation channel, difference channel, and this is azimuth difference channel, and this is sum channel. In that case, we have four hybrid junctions, as you can see, and the sum channel will simply give sum of all signals coming from four antennas. But the difference signal in elevation is going to be the sum of the BD, so sum of BD minus sum of AC. So the signal here and here are simply processed, and the difference is taken to get the elevation angle, or to get the elevation angle error signal. For the azimuth, we use AB. So for the azimuth, we use AB and DC, okay, CD. So the difference between these two sums will give us the difference signal for azimuth angle. So we got then two error signal, angle error signal. One is elevation and one is azimuth. And in parallel with that, we got some signal, which is coming again from the mixer, and then IF amplifier, amplitude detector, and video amplifier, and then we got the range. Okay? And note that we got an automatic gain controller right here, which is used to tune the signal power according to the range of the target. So for the targets near to the antenna, since the power is big compared with the targets at far distances, there should be a control or attenuation or amplification, usually attenuation. So AGC is used to attenuate signals coming from nearby targets. Okay. It was amplitude comparison that we have discussed in previous slides. Now let's see phase comparison. So instead of the signal amplitudes here in phase comparison monopulse, we use the phase of the signal. And this is sometimes sometimes called interferometer radar or direction finding system. It's based on the idea that if we use two antennas separated by D, and if I know the wavelength of the signal, then a signal coming from an echo signal from the target, the direction of the echo signal from the target can be calculated using this formula. Okay, so the theta here simply, that's the phase difference. So sine minus 1 d lambda over 2 pi d. Okay, how do we do this? We simply take the bore side of these two pair of antennas like this. That's the bore side. And if the target is exactly at this bore side, then we can get zero difference. If the target is just moving into up or down, then we get phase difference. Why? Because if there is an angle here, let's say theta, then we simply get a triangle here, right? And the signal coming from the target into antenna 1 and antenna 2 will have different distances. When there is a distance difference, we got a phase difference. So if I measure the phase difference, and then I can determine angle from this formula. The idea is quite easy. We measure the phase difference and then use this formula. I know D, I know lambda, these are fixed. Since these are fixed, then I can determine theta from this formula. Okay? Mostly there are more than two antennas, of course, in order to remove any ambiguity. There are some ambiguities in here. And this is a very mature technology, and it's been used in many direction finding systems. Okay, as I talk about acute angle, I said that in the next slide we'll be talking about optimum acute angle. And here is the slide that I'm talking about. Here on the right-hand side, we have the figure. Remember the acute angle. We got the bore side here. Okay, let me again remind you. This is the bore side. Okay, so antenna is like this, let's say, and we have two feeders, for example. And since they are positioned from the center, then there are going to be two beams. This is beam 1 and beam 2. Here is the bore side. And this angle from the bore side to the center of the beam is a secant angle, okay? Or this. So higher the secant angle, as you see, higher the signal difference, okay? And the amplitude of the different signal will be higher if we increase the secant angle. If we increase the secant angle, however, there is going to be a reduction in the received signal power, because the antenna pattern, as you see, the pattern factor will be considered, and it's smaller when we take the secant angle large. Okay, on the right-hand side here, you see the two curves, one for conical scan, the other one is monopulse. Here we have half power beamwidth of the antenna. Again, let us remember half power beamwidth. Here is the antenna pattern, let's say. Pencil beam antenna. Okay. And here is the center. Now, if this is the peak value, let's say P dB, the beam width is measured 3 dB down. So P minus P minus 3 dB. Okay, so I take this point and then this point and then measure the angle. Yeah, that's going to be the beam width, 3 dB beam width of the antenna. Usually these are pencil beam antennas that are used in tracking radars. So narrow band antennas. Now the secant angle here, theta q, is normalized by this beam width of the antenna. So you can see when theta q over theta v becomes 1, this means that we got a secant angle equal to the, which is equal to the beam width. Now here, as you can see, the secant angle is always less than beam width, starting from point 1 goes up to 0.7. So about 70% of the beam width. The optimal value of the secant angle from this picture is shown that it's somewhere about 0.3. So if I take 31 theta b as the secant angle, then I will get the highest slope of the error signal. I mean, the variation of the difference signal has maximum slope when we get the secant angle as just 30% approximately of the beam width. Okay, so what other parameters here are critical? Beam crossover. Beam crossover is the loss from the I mean the difference between the peak value of the beam and the crossover the two beams. So let's show it here. Okay, let's say this is beam 1 and beam 2. Okay, so here is my crossover actually, and here is the peak value. Let us show it with different color. Here's the peak value, here is the crossover. So this difference. When I increase the secant angle, so the angle from here, then we expect this crossover loss, increasing crossover loss, right? So when I increase the secant angle, the crossover loss increases, which means that the received power reduces by crossover, beam crossover. So that's going to be a problem. So increasing secant angle may not be a good idea due to this beam crossover and also the slope of the signal. So there should be an optimum value, and this seems that 30% of the beam width of the antenna is the optimal value for the secant angle. Okay, now the last subject was limitations to the tracking radar accuracy. And here we'll be talking about 4 types of errors, source of errors: glint or angle noise, receiver noise, amplitude fluctuation, and servo noise. Glint or angle noise affects all tracking radars, especially at short range. Okay, this is for short range. And the receiver noise affects all radars, especially long range, where the signal power is small. And the amplitude fluctuation may affect only conical scan and sequential lobbing, as the two tracking radars should move the antenna, should rotate the antenna or switch between the beams. Then there's going to be an amplitude fluctuation from beam to beam or position to position. That's a problem. But that's not a problem for monopulse, as in monopulse, all beams are created simultaneously, measurements are performed simultaneously, so there's going to be a constant error in monopulse radar. On the other hand, servo noise, which is about the mechanical instability of the servo mechanism system for the antenna. Okay, and there's a constant error from this. Now, if we try to evaluate this, glint or angle for short distances, receiver noise for long distances, a problem for long distances. Amplitude fluctuation is a problem for conical scan and sequential lobbing, but not monopulse. For monopulse, there's a constant error. And for servo noise, there's a constant error. Okay, what is about glint or angle noise? There are some other terms that you might come across. Angle fluctuation or angle scintillation. It's about the targets, actually. When we illuminate targets, the electromagnetic waves interact with the target. And if the target is large and if there may be discontinuities or composite materials, there's going to be different signals created by the target, and the echo signal will be composition of these signals. Okay, this causes a non-uniform phase at the planar aperture of the radar. You may imagine a composite signal of cosines, many cosines with different angles and amplitudes. So if we look at the phase, then there's going to be no uniform phase. This causes error at the receiver, especially for short range, very short range. The phase difference is higher, which causes fluctuation, okay, at the receiver receiving signal phase. This is evaluated. This can be measured an angle noise because we are here trying to estimate the angle. If there is a phase change in my signal, this simply cause angle error. Okay, receiver noise. It's one of the well-known source of error in almost all radar systems or communication systems. We are not going to derive anything new here, but we just use an equation derived by Howard. How to receiver noise can be taken into account in the tracking radars. And Howard has derived an error function here, which is given in terms of receiver noise, okay, along with some other parameters. For the parameters here, K is a constant. For monopulse, it's taken 1. For conical scan, it's taken 1.4. And theta B is the half power beamwidth of the antenna that we have already described in previous slide. And Ki is the slope of the angle error signal we have already shown in the previous figure, as you might remember. And B and tau are known parameters, bandwidth and pulse width. And FP was PRF, as you know, and beta N is the servo bandwidth. So that's about the rotation system, servo system, used to rotate the antenna. Okay, once all of these parameters are known, and then I can estimate error in angle measurements due to the signal to noise ratio. So the noise simply. So this is one of the most important slide of this of today's lesson. It's about comparison of angle tracking angle in conical scan, sequential lobbing, and monopulse. And we can see the sources of error: length, receiver noise, amplitude fluctuation, and servo noise. And here in this figure, you can see relative radar range here. So we are not giving any unit, just normalized. If this is, for example, 10 nautical miles, we talk about 100 nautical miles and 1,000 nautical miles. And in the other axis, we have relative RMS angular error. Okay, error, RMS error in angle. From, again, not a unit is given here, 0.01 to 0.1. So 1% to 10%, you can imagine. Now, here we got two curves, A and B. A is conical scan and sequential lobbing. B is monopulse. Okay, so we expect, we would like to get a small error, which means that monopulse is quite good compared with the conical scan and sequential lobbing. But at some distances here, for example, and here, the three trackers have similar performances. There is a very little difference. Okay, for example, here there is a difference, but quite small. For very short range, both methods, or conical scan, sequential lobbing, I mean, three trackers, conical scan, sequential lobbing, and monopulse, have similar performance. Their errors are the same. But at mid-range, you see, monopulse is quite much better than conical scan and sequential lobbing. The reason for this is about amplitude fluctuation, as you can see. In conical scan, we got amplitude fluctuation. In sequential lobbing, we got amplitude fluctuation, because these are not the tracking system which use simultaneous beams. Okay, they are switching between the beams, or they are rotating the beams. So there is going to be amplitude variation when the beams are switched or when the beams are rotated. But in monopulse, since there is no motion among the beams, all beams are created simultaneously, the received signal are measured simultaneously, then there is almost no amplitude fluctuation expected, which is the advantage of monopulse. On the other hand, servo noise is a problem for monopulse, as it is a problem for conical scan or sequential lobbing. When we look at the short distances, we see that the main constraint or limitation to the accuracy of the monopulse is angle fluctuation, glint. Okay, as we have described in previous slide. For large distances here, we see that the receiver noise is a main limitation. to the accuracy of the tracker. It's relatively better in monopulse, but that's still a problem for monopulse. Okay, so this is how we evaluate this figure. So here is a problem from the textbook. Please study, attempt to solve this problem, and then let's talk about in the office hour next week. Okay, that's the end of the presentation. Thank you for listening.